Welcome to our video module on quantum mechanics. Today, we'll be talking about the WKB approximation. First, I'd like to start off with a quick review of some of the potential profiles we've looked at already. First, there was the infinite square well, and the ground state of that looks something like this. Soon afterwards, we looked at the harmonic oscillator, and the ground state wave function for the harmonic oscillator looks something like this. And while we've looked at a couple other potential profiles, we've been somewhat limited in exact solutions due to the complexity of the wave function equations. That led us to perturbation theory, where we could look at small changes in potential functions that we already understood and get close estimates of the wave function and especially of the energies. However, what we haven't been able to do is look at potential profiles that say look like the bottom part of a trapezoid, or look, like a V, or more substantively, look something like this. The WKB approximation allows us to identify wave function and energies for drastically different potential energy profiles as long as we follow a simple guideline. To explore this further, let's review Schrodinger's equation. As you can see, I've written it in such a way to make E minus V explicit. If I wanted to take it a step further, I'd define our momentum P in classical terms is the square root of 2m times the quantity E minus V. And we've worked enough with this equation that we know that the wave function will be of the form a e to the I phi x. Now let's take a step back and look at what actually happens to a wave function in a sample potential profile. In blue, I've drawn the potential profile, and in gray, we can see the energy of some wave function. Now I'd like to draw what the actual wave function would look like and see if we can make sense of it. So in this case, we're looking at what happens as E minus V decreases. First, let's take a look at the wavelength of the wave function. If we compare the wavelength before the slope of the potential function with the wavelength during the sloped potential function, we see that there's a big change. In fact, the wavelength goes up. And a quick reminder that the wavelength is inversely proportional to the momentum. However, we note something else is happening. The amplitude of the wave function, once E minus V starts to change, also changes, and in this case, it goes up. So the amplitude in green increases. Or if we sketch that out on the wave function, we see something like this. Now look up to the Schrodinger equation. We can see that the Schrodinger equation is explicitly dependent on E minus V. As that E minus V goes down, that's going to affect our wave function that's the solution. And in this case, we know enough that that will decrease the curvature, thereby increasing the wavelength. So in other words, the wavelength changes because E minus V changes. So why does the amplitude change? Well, the logic here is similar to what we saw when we studied perturbation theory, that if we can make a relationship between the wavelength and the momentum, that tells us that as the wavelength goes up, such as what we might see right here, the momentum will go down. Well, if the momentum is going down, that means there's an increased probability of finding particles in an area with lower momentum. They're going slower, they're spending more time there. So by this logic, we know that the magnitude squared of the wave function is going to be increasing, so we know that the amplitude of the wave function itself will increase. Here's where we come to the WKB approximation. The exact solutions for scenarios like this are simply too convoluted and mathematically difficult. However, if we make one small assumption, we can establish a wave function equation that's actually manageable. Our assumption is that the change in the potential is slow compared to the wavelength of the wave equation. If we wanted to put this in more quantitative terms, we'd say that the magnitude of dv dx is much less than 4 pi e minus v over lambda. And if we make this assumption, we can derive the form of the wave equation. C over root p e to the I over h bar integral of p dx, where p is a function of x. This is the WKB approximation. And I should note that the critical step that allows us to make this assumption is we say that the second derivative of a is negligible. Now let's scroll down and give you a problem to play with. Once again, I've drawn the potential profile in blue. Above it, I put the energy of the wave function. And what I'd like you to do is put the video on pause and sketch out what you expect the wave function to look like from this potential profile. So feel free to put the video on pause, and I'll resume our lesson in about 5 seconds. Here I've drawn out an approximate sketch of what the wave function should look like. So while my sketch is a little sloppy, you can see that the wavelength doesn't change when e minus v is constant, and that the wave function after the little step up in potential is the same as the wave function before. And hopefully yours looks fairly similar. In summary from today, we've really gotten a chance to look at 2 things. One is we get a feel for how a wave function acts in a changing E minus V environment, as long as the wavelength of the wave function is very small compared to the change in the potential. The second thing we've looked at, here let's go back up. The second thing we've looked at is we've been able to see that with that assumption, we now have a new form of wave equation that can help us with drastically different potential profiles. Thank you for joining me. I look forward to talking with you next time as we explore what happens if E minus V is negative.